My name is Marcelo Villa, and I'm going to talking about modern geospatial data science in the cloud with Nebari. I'm guessing some of you might run geospatial data science using Python, right? Some of you. And do you know what Nebari is? Have you had any interactions with it? So before diving deep into what Nebari is, and I'll be doing a demo at the end, I want to first introduce me, just so you have some context on where I'm coming from and why I think Nebari might be a very beneficial platform to run geospatial workflows on. So I'm an ecologist with a background in remote sensing. I started doing burnt area estimation, doing things in the Colombian savannas, and then I started working on some other projects like forest monitoring and flood detection. And now I'm working as a cloud infrastructure engineer at Quantside, where one of my main tasks is maintain Nebari as a platform and an open source package. And the reason I pivoted from being an ecologist interested in remote sensing to doing cloud infrastructure engineer was basically that I wanted to be able to empower people to focus back on science. Because I'll be telling you more about some challenges that I faced and I know that other people face when doing geospatial and data science in general. But I feel like there are many occasions where people struggle getting the implementation right, whereas they should be focusing on science, what they really want to answer in the research. When I started doing remote sensing, things were much simpler. I was dealing with very small data sets, just a couple of images, small regions in my country, not very long time series. It was less complex problems. I was using analysis-rated data. I didn't have to care too much about pre-processing, just maybe some clips here and there, reprojection, resampling, but that was most of that. It was mainly just one user, which was me, on my computer, just using a local environment, using Conda, because as you might know, I was using GDAL, and installing GDAL without using Conda, or at least at the time, was very painful. So that was actually my first introduction into Python and Conda, using GDAL. And then in the worst case scenario, I would just rent or launch an EC2 instance in the cloud, AWS, transfer my local files there, download whatever data I needed to, just process that in the cloud, and then bring the results back, which is arguably not the best practice, but it was my first exposure to the cloud too, and I was pretty excited of what you could start doing in the cloud. And then as I started moving on onto more complicated problems, things started getting more challenging and more complex. I was working with bigger data sets. At my last company, we processed the whole Sentinel-1 catalog and the whole ALOS-1 catalog too. It was more complex problems too. We were not just doing analysis-ready data. We were doing RTC. We were doing time series analysis. We were running different machine learning models. We were running training. We were doing inference. It was multiple collaborators and bigger teams, so it was not just one person anymore. It was different teams, different organizations, making sure everything was shared and everyone could access everything. And it was not just my local computer anymore. It was a distributed computation. It was using the cloud. It was leveraging everything of these different cloud providers and cloud services to be able to actually process those amounts of data. And while doing this, I realized that there are some current challenges in geospatial and in data science in general. So one of the first challenges is effective collaboration. It's not very easy to have everyone use the same platform. You need to have a centralized way of giving people computational or computing resources. You have to have a way of sharing data, make that publicly available. You need to have a way of handling permissions, handling all of these. You need to ensure that your workflows are reproducible if you want other people from your team or from anywhere else to be able to run that. But also because you're not working in one machine anymore, you want all the machines that are running your workflows and your processes to be actually able to run that, right? And on top of that, you're also taking scalability into account because now you have multiple users. It's not just one user, one computer. You have bigger teams. And you also have lots of data, so you just don't want to have one machine process everything. You might want to set up clusters on demand for everyone. And at the end, if we're taking these three first challenges into account, it all relates to having the infrastructure on where to run that, right? Because you need a platform, you need a platform that scales, you need to handle data, And that entails, of course, deploying infrastructure, but also configuring it and also maintaining that. And that's actually one of the biggest challenges. How to address some of these challenges? I think on the first hand, we have the modern Python ecosystem, and it partially deals with some of them pretty nice. You have very nice abstractions like Xarray, which is amazing because if you use something like SAR, you can chunk your data, and then you can use Xarray to lazy load that data. And then it's beautiful because you just have the metadata, and you can use something like DAS to actually upload all the computation to a cluster, which is beautiful. And then you have some other specifications like Stack, which makes everything much more easier to access data. When I first started working with remote sensing, I was using Modis data, and I used the Appears API, if that rings a bell to anyone. And it was a NASA API to discover Modis products, and it was not really bad. It actually was really cool. But you had to query your area of interest, put some parameters, and then you would get a job submitted to NASA, and they will get back to you in a couple hours with the data. Stack and cloud providers hosting data make these so much easier because you just have to query the data and bring that back, and that's it. The data is already there. You can query all the metadata, and you can just pull that out. And that makes everything amazing, right? And then you have all these different modeling packages from standard stuff like SciPy to AI like PyTorch, TensorFlow. And on top of that, you have all these very nice plotting ecosystems, especially with the HoloViz ecosystem, where you can just upload all the computation for the plotting and then put that in, or bring that back to actually plot that locally. And additionally, you have the whole Jupyter ecosystem, which makes interactive computing very nice. You have Jupyter Hub for people to request their own on-demand servers. You have Jupyter Lab and all the Jupyter Lab extensions that people have built on top of that. And then on the other hand, we have the cloud ecosystem, right? We have all these major cloud providers. We have Google Cloud, we have AWS, we have Azure, and we have all these different tools from container orchestration systems to monitoring, to logging, to metric gathering. You have all these infrastructure as code approaches and tools, and then you have deploying tools like Helm to deploy services. But I think there's one challenge left, and it's how to actually bridge the gap between both ecosystems, because cloud is being made accessible, that's true, and we want a way to be able to run modern Python, geospatial data science, and even R or any other language on top of this infrastructure. But it's not always entirely clear on how to do that. When you start setting up your own infrastructure, you will encounter that you need to also take care of storage provisioning, node sizing and scaling, things like ingress setup, networking, user authentication, and all these different things that quickly become very overwhelming, right? Because you were a data scientist, or you were a person that was just doing forest monitoring, and then you found yourself actually trying to set up a Kubernetes cluster. How did you get there? I actually got there while pivoting, but I enjoyed my journey here. But I see that there's a lot of potential for those platforms that offload some of those overwhelming tasks so the users can get right away into that. And there are certainly several alternatives, and I want to talk about Nebari being one of them. So Nebari is an open source data science platform that we have developed at Quantside, and it's built for scale and designed for collaboration. Basically, what it allows you to do is deploy your own platform on top of one of the major cloud providers or an existing Kubernetes cluster, and then it will deploy all these different services like computation. You will have access to Jupyter Hub, so all of your users can request on-demand computation resources. You have tasks to scale your different computations to. You have Argo workflows, and you have Conda Store for environment and dependency management. You have all the whole cloud monitoring stack based on Grafana, Prometheus, Loki. Then you have Keycloak for authentication, user management, and you have other applications like VS Code and the ability to publish applications and share that with colleagues like Panelabs, Streamlead, Plotly, all these different kind of stuff. Why use Nebari for geospatial? So Nebari was not intended with geospatial as its main use, but I certainly got to know about Nebari because I was doing remote sensing, and I started using Nebari just to prototype stuff, collaborated with a couple of colleagues, used Dask, launch everything just from a web platform that I didn't have to do anything deployment-wise. So it is a collaboration platform, meaning that whoever has a team that wants to be able to access these just has to deploy the application or the platform. And then everyone that is being granted access can join that. That also means that anyone who wants on-demand computing resources can just use that using Jupyter Hub. And admins can just configure whatever hardware and software configurations they want for their users so they can actually use that. Then you also have environment and dependency management using Condastor. I'm not sure if anyone's familiar with Condastor, but it's a way to build and share environments in different ecosystems, including cloud ecosystems. And you have Docker to use all the runtime dependencies or system packages that you wouldn't find in a Conda environment. And then another thing is that it gives you the ability to bring computing power close to the data, because you can deploy these on any cloud provider on whatever region you want. And one of the things is, if you're using a lot of data from, say, ASF, or maybe you're using Element 84, you might want to have your cluster be running in US West 2 rather than somewhere else, because then you don't incur an egress cost, or they don't if they put that out for free. But it's also going to be way faster, especially if you have your own data too. And then scalability. So as I mentioned, we have all these very cool packages like Dask for offloading computation. So if you pair that with SAR and you pair that with Xarray, it becomes very nice to be able to scale things up. And not just in terms of one user scaling one workflow, but also having multiple users do geospatial at once. So you could have 10 users, 100 users, all of them using the same platform. And then it's also customizable, because everyone knows that every single team has different needs. Some people have other requirements. Some people might need different environments, different dependencies, the different authentication systems. Some people need more privacy. Some people have more open policies. But Nebari works on top of a plugin-based system where you can deploy your own plugins. You can deploy extra infrastructure if you might want that. So that's how it works. How do you deploy Nebari? Basically, we have a CLI. Anyone can install that. It's a Python package that will guide you through creating a Nebari config file, where you will put all the specification, what kind of nodes you want, what kind of Jupyter Hub profiles you want, even if you want to include GPUs. Where do you want to deploy these? Do you want to deploy these to AWS? Do you want to deploy these to any other cloud provider? What region do you want to use? And then using that config file, you can deploy these. These under the hood will basically use Terraform as an infrastructure as code approach, and then we'll use Helm on top of that to deploy all the services. And at the end, you will have a web platform that anyone with the right access can just go ahead, and I'll show these in the demo. And we also implement some kind of CI/CD functionality where admins or people managing the platform don't need to do that from their computers or their laptops. They just need a GitLab or GitHub repo. And anytime they add something new to the config file, like for example saying, hey, we're upgrading our Kubernetes version, or we are creating a new node because we need GPUs for this particular kind of thing, well, it will take care of that automatically. So at the end of the day, the value proposition of Nebari is having a DevOps approach for non-DevOps people. Just as I said, doing the heavy lifting for you, you not having to actually do all the infrastructure yourself, setting all the networking stuff and setting all the services or configuring them by yourself. How are people using Nebari? There's a lot of people using it in research in industry, just giving their teams a platform and a way to access quickly computation resources, share their data, share their workflows. Also government are using it quite a bit. Education training is where I see a lot of potential, especially, I'm not sure if you have gone to any workshops in tutorials or in conferences, but people usually need to install things themselves, and that takes some time. And maybe if you have a GPU tutorial, not everyone has a laptop with a GPU, so you have to figure that yourself. And you start losing vast amounts of time where you would be supposed to be teaching just for people to configure everything, even if you ask them to pre-configure stuff. So we have run a couple of big trainings or big tutorials. We did one in SciPy this year and another one at PyCon, where we just had 80, 100 participants. We deployed Nebari specifically for those two occasions. We had GPUs enabled. Everyone came to the room. They sat. They just opened Nebari, registered, and launched GPU in a question of 5 minutes. So, and everybody had the material. Everybody had the Conda environments they needed to use. And then community projects and open science. I think in geospatial, if you are familiar with ECIP, those are the Earth Information Science Partners. They have a Nebari deployment. So several people from different organizations across the US were using it to just do different kinds of research in open science and community projects. I'll say that there are some alternatives, not geospatial related only, but for example, there's Digital Earth in all their flavors. You have Digital Earth Africa, Digital Earth Australia, and Digital Earth Pacific. It seems that Digital Earth, any of these three gives you way more tools to do geospatial kind of stuff. You have access to more data, but it's a similar kind of concept where you get access to a platform and you have a way of launching resources on demand and doing your geospatial science or geospatial data science workflows there. There's also 2I2C. They basically deploy platforms for their users, Jupyter Hub on top of cloud providers, very similar to these, but they host them, or they host that for different clients, and you get charged per user, I think. And then you have all these different software as a service products like Google Colab, CoCalc, SageMaker, and Saturn Cloud, where you can just register and you can create an account, and then you get some kind of GPU access or CPU, some configuration, and you have some credits, and then if you want more, you have to pay for those. And on the other hand, there's also always the possibility of doing your own in-house development, right? That's probably how some of these started. Somebody just wants to deploy these for their own organization. They start learning Kubernetes, they start doing these. The advantage is that it's very flexible. You can do whatever you want and target or tailor your specific needs. But of course, it comes with a lot of resources and time that you might not have. I guess the difference between the first three and Nebari is that with Nebari, we're not hosting anything for you. You're deploying your own platform in your own infrastructure, so you're fully in control, which, depending on your use case, might be beneficial or not. That's for you to say. And then where to begin with Nebari, we have, this is the docs page. We have a GitHub repo where you can just see everything, all the Terraform code, how we are setting up and configuring the cluster, how we're deploying services. And we have community meetings every other week on Tuesdays. So if you go to the docs, you can also check the calendar event, and you can potentially join if you want. That would be awesome. And now I just want to show a very quick demo and see if I can get you interested in this. So I deployed Nebari here just for FOSS4G. I deployed it on AWS and US West 2 because I'm planning to access one stack catalog that has data exposed in US West 2 on AWS. It's one of the Element 84 data sets that they have. This is how Nebari looks like when you enter that. You can use Jupyter Lab, you can use VS Code, you can go to your environments, for example. And for the environments, you have different namespaces. So for a global namespace, whoever has access to these, I just created a FOSS4G 2024 environment with all these packages. So that means that if any one of you had access to this platform right now, to my deployment, you would be able to start a notebook or a Jupyter Hub server and just use this environment right away. You wouldn't have to bring your own environment. And of course, you can create your own private ones, and you can delete them, edit them, create new builds. I have a server already running because I didn't want to wait too much time. This is actually, it's running on an instance that was just created when I requested. So it's not our instance that is always running. It's auto-scaling. So if you have 100 users, depending on what kind of resources you requested, that will launch all those instances. And I have a very small example. Let's imagine I want to do like a normalized difference moisture index for a time series for an MGRS style. But I know that's probably going to take some memory and some CPU usage, and I want to just upload that computation to Dask, retrieve that back, and just do a very simple visualization to get some ideas on seasonality. So I already launched a Dask cluster because that also might take a couple minutes more than I would have for this demo. It's currently running 10 different workers. Each worker is one pod on Kubernetes. So basically, we're running one pod for a Jupyter Lab here. It has 8 gigs of RAM. But I'm also running 10 other workers that's just not Jupyter, it's just Dask, and it amounts to 80 gigs of RAM, what I have available right now. So I have this client here, and now so basically, this is a very common workflow in what I would say it's modern geospatial Python. I'm just using PyStack to open a catalog. Oops, it seems that, well, I might have to run everything again, apparently. I'm not sure if this is still running. Sim it is. Okay, let's just restart this, very easy. Okay, I'm just saying I need 10 workers and I can do 16 maximum, but that could be 20, 40, whatever you would like. Then I'm gonna try to run this again. Okay, so I have the dashboard here. And it's actually starting some other workers. That previous cluster might have just been idle for too long while I was talking. Now I'm going to run a query. This is a MGRS tile in the Serengeti in Tanzania. And I'm going to search that catalog. And I'm, whoops. Catalog is here, sorry. So I query that, and I'm just going to use GeoPandas to show you where those tiles are. Hopefully it doesn't take too long to render. Okay, that's perfect. So those are all the outline scenes that I can gather. That's that particular tile in Tanzania. And then I'm just going to do basically everything or the same thing that everyone has talked about. We use ODC Stack to basically grab all those items and load that into a X-ray data set, right? For me, it's beautiful. I'm sure I'm not the only one, but these have made my life so much easier. I'm specifying some chunk sizes because I'm not actually loading all the data. I'm just loading the metadata and doing the lazy load. And this is what the data set looks like. So it's a 2,000 by 2,000 by 285 time steps. I'm actually just using 3 different bands, near infrared, and I'm also using the scene classification to compute some masks. So that's exactly what I'm doing here. I'm getting rid of all the shadows and all the node missing data and all those pixels. So I'm masking the data. And at the end, I'm computing NDMI, so this index here, and I'm offloading that to Dask. So now we should see Dask fully running everything on this. So otherwise, you would see a lot of memory being used here, and probably 8 gigs of RAM wouldn't be enough. And as you can see, this is reading data, and it's actually going to do all the division operations to get the index. And those are all the workers streaming all that data. Shouldn't take too much. It's not a very long time series, and I also resampled, or I specified that I would read the data at 40 meters per pixel, 40 by 40. So, but because I can't keep doing other stuff because everything's being uploaded to the cluster, so I'm doing running a vegetation mask just to make sure I'm only plotting this index for vegetated areas. And I'm doing a resampling both in time and space, so I'm just grabbing every 100 by 100 pixels and just computing the mean for that. And the reason I'm doing that is because I want to use HoloVs to plot the time series for every 100 by 100 square and see how that tendency looks like. So I'm just doing that, and I'm defining some outlier using the IQR method, and then I'm filtering those out. And at the end, I'm just creating some curves using HoloVs, and that's what I will plot here. So, and if we go, these are all the operations that are happening right now. I didn't have to take care of any of the infrastructure when doing this. It was just logging in, launching a server, launching a Dask cluster. Everything's being taken for me on my behalf. So when I started doing these with Nebari, it was, oh geez, let's use this for whatever I have to do, all the computations, because it makes things certainly much easier. And I guess that would be the same for any other platform when you don't have to deploy that yourself, and your scientists can just go here and start implementing their own workflows. And this should plot any second now. It's bringing all the data back from the cluster. You see it doesn't amount to much. It's almost there. And this is how, I don't know, it's probably a couple hundred lines that we plotted. And this is like showing some seasonality and some clear outlines in the last 3 years in the Serengeti vegetated areas, or what they count as vegetation. And we can do a box plot and see some seasonal changes. But yeah, that's basically it. There are a lot of more stuff to Nebari, like, for example, having Grafana for monitoring stuff, or monitoring users, monitoring resources. But I just wanted to run a small of what I would call modern workflow, and show you how easy these can be when you already have a platform to run that on. So yeah, thank you.